So this is going to be our first video lecture on radiation, and we'll be having 3 of these lectures being recorded, and this is going to be the first one where we introduce radiation and some of the properties of radiation heat transfer. We'll have a few examples as well, so make sure you follow along, and at the end of the week, when I come back to Qatar on Sunday, I'll be able to post all of the slides. For now, I'm just going to post these videos. If you have any questions about any of the things that we go over today, feel free to send me an email, and I'll make sure to explain the best I can over email, or you can wait till Sunday, and I can explain on Sunday as well. So let's go ahead and get started. So the radiation we've already covered before in the introduction section. So unlike conduction and convection, the transfer of heat by radiation does not require the presence of an intervening medium. So the most common example that we can go over is if you have a container with nothing inside, not even air, you will still have radiation. And if you've done the heat transfer lab, you'll remember our radiation heat transfer experiments. We used a vacuum pump to remove any air, and we assumed all the heat transfer to be through radiation. So you do not need any material for radiation to occur, and that's one of the major differences between radiation convection and conduction. So radiation is the energy emitted by matter in the form of electromagnetic waves. In this course, we are mostly looking at thermal radiation, and this covers parts of the ultraviolet spectrum, visible light spectrum, and the infrared spectrum. So this is the electromagnetic spectrum, and there are different types of waves. You might have seen this in physics. We have gamma rays, X-rays, ultraviolet, and then we have the visible light spectrum, and infrared, and then microwaves. So we're just interested in this spectrum here, which is going to be our thermal radiation heat transfer. This is what we're focusing on. Gamma rays, X-rays, and microwaves is not something that we're interested in. So let's start our discussion with a black body. So a black body is an ideal surface having the following properties. It absorbs all incident radiation. It's a perfect absorber. And at a specific temperature and wavelength, no surface can emit more energy than a black body. So a black body is an idealized body which absorbs everything and emits the most it can. And we'll get to those equations in a bit. So we have the black body emissive power that's given by the Stefan-Boltzmann's law, where EB is equal to sigma Ts to the power 4, where we've introduced sigma in module 1 to be the Stefan-Boltzmann's constant, and we have Ts, which is the surface temperature of the object. And the units on EB are watts per meter squared. And we can get the wattage or the power by just multiplying by the surface area. And we'll see this form in a few more slides. The main note that I want to make sure that you guys are aware of is always use temperature in Kelvin when using the equations for radiation. All of the equations are use temperature to the power 4. So if you're using degrees Celsius, you're going to get a different value than if you use Kelvin. So it's important to make sure that you use the correct units, and the correct units for any radiation-related problem is going to be Kelvin. So if you have any problem that's related to Kelvin, related to radiation, make sure you convert things to Kelvin right away. So here's a quick example on a black body. And this is going to be a very simple example just to get us started with radiation. So it says, consider a 20 centimeter diameter spherical ball at 800 Kelvin suspended in air. assuming the ball closely approximates a black body, determine the total black body emissive power and the total amount of radiation emitted by the ball in 5 minutes. So here we have our Ts to the power 4, or our Ts, surface temperature, and we know it's a black body. Okay, so we can use the equation from the previous slide. And we have the total black body emissive power. We have our Ts. We have sigma, which is a constant. So we can use the equations, which I'll show in a bit. We also have the diameter. This gives us the surface area. And it says the total amount of radiation emitted by the ball in 5 minutes. We have this delta T. Okay, so we should have everything that we need to be able to calculate the parts A and part B. So the black body emissive power is given by EB is equal to sigma Ts to the power 4. We saw that a few slides ago. And it's just plugging in the numbers. The main thing that I want to point out is this has to be in Kelvin. So if I've given you 800 degrees Celsius, you'd have to add 273 to make sure that this is in Kelvin. So just this simple calculation, you get the emissive power. And the amount of radiation can be found by calculating the amount of heat transfer over an amount of time. So Q is just going to be EB, it's a black body, times the surface area. And this gives you the amount of heat transfer, or the heat transfer rate due to radiation. And we find that to be 2.92 kilowatts. We can do the same thing with the amount of heat. So Q is just Q times delta T. So we have our Q, and we have our delta T, and we can get the amount of heat transferred through radiation, which is 875 kilojoules. So this is just a simple example to get us started with radiation heat transfer. What I want to make sure is that you're aware of, again, the temperature, and you're aware of sigma. Sigma is not something that's provided in the exam, that's something for you to know. Sometimes some calculators have it saved as a constant in your calculator. You can double check if that's the case with your calculator. Otherwise, you'll have to know it for the exam. So the amount of heat that can be transferred by a black body depends on both temperature and the wavelength. So depending on the wavelength of the electromagnetic wave that we're looking at, we could have different amounts of heat that's being transferred. In the previous two slides, we just took the temperature and assumed the whole wavelength for thermal radiation. But sometimes we might want to look at specific wavelengths, and we'll determine how we can do that in the next few slides. So you can see from this slide, on the x-axis you have the wavelength, and on the y-axis you have the amount of power that can be emitted. So the amount, as the wavelength changes, you can have different amounts of power being emitted, and you also have the dependence on temperature. So each one of these curves are for a different temperature. So you can see how the emissive black body power changes based off of the wavelength and the temperature. So what we'll look at in a bit is if we're looking at this temperature, for example, how much power is going to be emitted between, for example, this wavelength and this wavelength. So that's one of the things that we'll do in the next few slides. So there is a dependence on both wavelength and temperature, and that determines how much heat can be transferred through radiation by a black body. So we know that the total amount of radiation from a black body can be calculated using the following equation. So this is just the form with surface area, so this is going to be units of power. We can also break down the amount of radiation for a black body into the amount of radiation for ranges of different wavelengths. So as we mentioned, we have a range of wavelengths that carry the different amounts of energy. So we might want to break that down into different wavelengths to see how much power is emitted for the different wavelengths. The total is just defined by this equation. So this is the amount of radiation heat transfer for a black body going from some zero wavelength to a specific wavelength. And this is just the integral of the areas that of the charts that we saw in the I think 2 slides ago. So there is an integration, but we're not going to do any integration, and I'll show you how we'll take care of these integrations. The fraction of radiation for a range of wavelengths can be found using the following equation. So it's just the total energy from 0 to a specific wavelength over the total black body radiation, and that gives you the fraction. So again, there's an integration here, but we'll show you in a bit how we'll take care of that integration. So we have seen how the black body radiation changes with temperature and wavelength. As I mentioned, it'll be difficult to do such an integration by hand every time, so the results are tabulated. So just like how we've seen many times in the course, results being tabulated, so such as the Biot number and lambda 1 and A1, or the complementary error function. We also have a table that does the integrations for us, and we'll show you that on the next slide. So we have the fraction emitted by a certain wavelength. These are here. So depending on what your value of lambda t is, you'll have different values of the fraction. And you can see as lambda t gets higher, it gets closer to a value of 1, which just means that you've covered almost the whole range of wavelengths. So the first step in any of these calculations is to calculate lambda t. And of course, the units are micrometers by Kelvin, where micrometers is usually used for the wavelength, and the temperature is used for Kelvin. So you find your value here, and then, so for example, if our value is 1000, you'll have a value of 0.0321. So this is going to be just calculating lambda t, comparing it with the table, and getting your value. Sometimes, of course, you'll need to do interpolation if your value is not here. And that's just the nature of using tables. So I believe we have an example on the next slide. Yeah. So charged coupled device image sensors that are common in modern digital cameras respond differently to light sources with different spectral distributions. Daylight and incandescent light may be approximated as a black body at the effective surface temperatures of 5800 K and 2800 K respectively. Determine the fraction of radiation emitted within the visible spectrum wavelengths from 0.4 micrometers to 0.76 micrometers for each of the lighting sources. So they want to know what the fraction of radiation emitted within the visible spectrum. So we have our from 0.4 to 0.76 micrometers. How much radiation is being transferred at these two temperatures, 5800 K and 2800 K. So we'll do these one by one. We'll start with the 5800 K, the daylight, and then we'll do the incandescent light at 2800 K. So for daylight, they gave us a temperature to be 5800 K, and our first wavelength was 0.4 micrometers. And then we can go ahead and calculate lambda 1t, which is 2320 micrometers times Kelvin. And we can calculate the value for the second wavelength, which is 4408 micrometers Kelvin. So again, If you remember the curve, it looks something like this. And we're just trying to find the fraction of radiation between two wavelengths. So it's going to be something like this area. Okay, where this is going to be your wavelength 1, and this is going to be your wavelength 2. Okay, so the fraction for lambda 1 is 0.125. And remember, this integration is from 0 to lambda. Okay, so lambda 1. So you're going from here all the way to lambda 1, and that gives you the value of 0.125. And then the second one is 0.55, which is from 0 to lambda 2. We don't want the values from 0 to lambda 1, and we don't want the values from 0 to lambda 2. We want the values in between lambda 1 and lambda 2. So to do that, we just calculate the difference. So we have f lambda 2 minus f lambda 1, and that gives us 0.426. So this area is 0.426. Okay. And this 0.125 is going to be all this area from 0 to lambda 1. And this 0.55 is going to be the whole area from 0 to lambda 2. So the blue area minus the green area gives you the red area, and that's what we want. So that's what we've done here. So this is the blue area minus the green area, and this gives us the red area. Okay, so we'll be doing something similar to this in example 3. So we want to make sure that we know how to do this correctly. Before we get to example 3, we want to do it also for the incandescent light. And it's the same procedure, but the temperature is a bit different. So the temperature is 2800 K, so we'll do those calculations. And we get 1120 micrometers Kelvin and 2128 micrometers Kelvin. And we get these fractions. The one thing that I want to make sure that you guys are aware of is how to go from these values to these fractions using the table. This is going to be one of the main steps, and it's important for you to know how to go from these values to these fractions. And again, the fraction of the radiation is the difference between the two fractions, and we get 0.87 or 8.7%. So that ends example 2. So now let's talk about radiative properties. So when radiant energy strikes a material surface, part of the radiation is reflected, part is absorbed, and part is transmitted. So rho is reflectivity, alpha is absorptivity, tau is transmissivity, and that all equals to 1. Okay, so it's each one of these is a percentage. So some percentage is reflected, some percentage is absorbed, and some percentage is transmitted through the material. And as you know, any percentage, sum of percentages should add up to 1. So we'll talk about reflectivity, absorptivity, and transmissivity, I think, on the next slide. There's a good image that shows you what they physically mean. So whenever you have any irradiation coming from some outside source and it hits a material, so this is called irradiation. And what happens is some of the irradiation is going to be reflected, okay, or bounced off the material. Some of it is going to be absorbed into the material, so the energy actually stays inside the material. And you have some energy that's transmitted through the material. So it goes through the material. So those are the physical meanings. And of course, doing just the energy balance, whatever energy enters the system has to add up to whatever is entering and leaving. So you have irradiation should be equal to the reflection plus the absorbed plus the transmitted, because that's where the energy is coming from anyways. It's all adding up to the irradiation. So that's for a semi-transparent medium. For an opaque medium in which nothing can go through, you have irradiation coming in, and then you have two sources of energy coming off the system, which is reflected from the body, and you have energy that's emitted from the body. And that adds up to what we call the radiosity. And this is emission due to radiation, so it's not related to the irradiation. Here you have some irradiation coming in, and then you have some percentage that is reflected. And that comes from the absorptivity, base of the reflectivity parameter. And then you have some from emission, which is based off the temperature of the medium. Again, this is just a summary of what we just discussed, and it's a good summarization of what's been there in the images. So for black bodies, rho is equal to 0 and transmissivity is equal to 0. So you have absorptivity is equal to 1, so everything is absorbed. As we mentioned before, it's the perfect absorber. Nothing is reflected and nothing is transmitted. It's all absorbed. For opaque surfaces, such as most solids and liquids, the transmissivity is equal to 0, so alpha plus rho are equal to 1. And we'll see later on in the lecture why it's important to know this relationship. So a black body is an ideal surface that has an emissivity of 1. Real surfaces are gray surfaces, and that just means the emissivity is between 0 to 1. As we mentioned, a black body is an idealized body or idealized surface where the emissivity is 1, and that's not going to be usually the case. You'll have a value between 0 and 1. The emissivity is a surface property, and the value depends on the surface. And the surface of a real object varies, so the emissivity will not be constant across a surface. And we have a graph on the next page which will show what that looks like. So here's a graph that shows emissivity versus wavelength. And as we mentioned before, black body has an epsilon of 1, and it's perfect. And a gray surface has some kind of epsilon, and you can see that that's a dotted line. A real surface, its emissivity is going to vary depending on the surface. So that's why you can see that it goes up and down and it's not constant. It just depends on the surface properties. So whatever epsilon that we use for a gray surface, it's like an average gray surface or average emissivity. It's not a fixed emissivity. It's going to be some kind of average because it varies with the surface. And the same thing with the black body or the radiation transmitted. It's going to, again, change depending on the wavelength. And you can see how a black body is going to be. It provides the most radiation compared to a gray surface. And you can see the gray surface has a nice parabolic curve, whereas a real surface, it's not that neat. It's going up and down around the gray surface, and that's again because the emissivity depends on the surface. The emissivity can also depend on the wavelength. So a surface may have different values of emissivities for different wavelengths. So you can see here, for example, from 0 to wavelength of lambda 1, we have epsilon 1, and then lambda 1 to lambda 2, we have epsilon 2, lambda 2 to infinity, we have epsilon 3. And you can see they're nice fixed lines, and those are going to be our average emissivities, whereas for an actual surface, they're not going to be fixed lines. And that's just because, again, due to a surface not being smooth. So the average emissivity can be found using the following equation, where epsilon lambda, depending on both wavelength and temperature, times the black body emission, which again we've mentioned before also depends on wavelength and temperature, divided by the total black body emissions. So we'll do an example that applies this equation so that you can have a good understanding of how to apply it. So we have the spectral emissivity function of an opaque surface at 800 K is approximated as the following. So you have epsilon, which is varying with the wavelength. So for wavelength of 0 to 3 micrometers, we have a epsilon of 0.3. From 3 micrometers to 7 micrometers, we have an epsilon of 0.8. And then from 7 to infinity, we have an epsilon of 0.1. And it says determine the average emissivity of the surface and its emissive power. We showed the equation in the previous slide, but now we're going to actually apply the equation now in this example. So this is our equation. It just looks a bit different because we have multiple integrations. So we have epsilon 1 for a range of 0 to lambda 1. We have epsilon 2 for a range of lambda 1 to lambda 2. Then we have epsilon 3 for a range of lambda 2 to infinity. And so we've done these integrations before, right? 0 to lambda 1 for the black body from 0 to 4, depending on the wavelength. And we said that that's going to be some fraction, right? If we include the sigma t to the power 4, that's just a fraction. And it's the same thing here. So this is just a fraction from lambda 1 to lambda 2, and this is a fraction from lambda 2 to infinity. So we did this in example 2, but this time is just to determine the average emissivity. So we have epsilon, so this simplifies to epsilon 1 times the fraction from 0 to lambda 1 plus epsilon 2 times the fraction from lambda 1 to lambda 2 and epsilon 3 from lambda 2 to infinity. So f of 0, if you look at the table, is just 0. So this simplifies to epsilon 1, f lambda 1. And this is going to be epsilon 2, f lambda 2 minus f lambda 1, similar to what we've seen in example 2. And f of infinity is just 1, so that simplifies to that, and we have minus f lambda 2. So using the tables and calculating lambda t for both lambda 1 and lambda 2, and then using the table to get f lambda 1, we get these values, and we can go ahead and plug them in and get the average emissivity for that surface. And then using the average emissivity to get the black body emissive power, we get 12.1 kilowatts per meter squared. So this example is just to show you how do we take into account changing emissivity for different wavelengths. And this is not a black body. Remember, the epsilon is not 1, so it's not a black body. This is a gray surface now. One thing that we want to make use of is a simplification called Kirchhoff's law. We have a large isothermal enclosure a large isothermal enclosure forms a blackbody cavity regardless of the radiative properties of the enclosure surface. So if we have a large enclosure, which is isothermal, it doesn't matter what the surface is here, doesn't matter what the radiative properties are, it still forms a black body. So if you have a large isothermal enclosure, it's a black body. And then what we can do is we can consider a small body of surface area AS, emissivity epsilon, and absorptivity alpha at temperature T inside the cavity. We're going to use this example to try to make things a bit simpler. So just remember that the large isothermal enclosure is going to be a black body, and the small body is going to be some gray surface with epsilon, with some emissivity epsilon and some absorptivity alpha. So the amount of heat emitted by the object is going to be epsilon sigma AS TS to the power 4. And the amount of heat absorbed by the object is going to be G is equal to alpha sigma AS TS to the power 4. And we apply an energy balance on the object. We have the energy emitted by the object and the energy absorbed by the object. We can cancel out sigma, cancel out A, and cancel out TS to the power 4. We get a simplification that says epsilon is equal to alpha, which makes things much easier. So that's what Kirchhoff's law allows us to do, to assume epsilon is equal to alpha. We do have a condition to use Kirchhoff's law. So it says, note that this relation is derived under the condition that the surface temperature is equal to the temperature of the source of irradiation, and it is cautioned against using it when considerable difference, more than a few hundred degrees, exists between the surface temperature and the temperature of the source of irradiation. So this is a simplification that assumes that the surface temperature is equal to the temperature of the source of irradiation. That might not always be the case, but it's going to be an assumption that we make so that we can use Kirchhoff's law. If there's a considerable difference, we're not going to be able to do this, but for the most of the problems that we will encounter, we should have no problem doing this. So if we assume epsilon is equal to alpha, we get the net radiation of heat transfer to be the following equation. Okay, so it's quite simple. We don't have to deal with any alphas anymore. We can just deal with epsilon. So the last thing that we want to go over is radiation intensity. Radiation is emitted by all parts of a plane surface in all directions into the hemisphere above the surface, and the directional distribution of emitted radiation is not uniform. The quantity that describes the magnitude of radiation emitted in a specified direction in space is called radiation intensity, and we're going to use spherical coordinates to define the radiation intensity. So we're going to go into a bit of math. It's going to be more of an introduction on radiation intensity so that we can apply these equations when we talk about the radiation view factor. So bear with me with the mathematics. Just try to understand what's going on so that when we get to view factor, you know what the view factor actually means and where these numbers are coming from. So as we mentioned, we're going to use spherical coordinates. So we have theta and phi to define where we are in space. And of course, we're going to have the radius. I is the radiation intensity, and we'll get to those equations in a bit. So a solid angle is a three-dimensional body. It's what we saw just in the previous slide. That looks something like this. Okay, so that solid angle is a three-dimensional body, and we're going to have to use it in order to be able to calculate the radiation intensity. The unit of a solid angle is called steradians. And the differential solid angle is related to the area and radius through the following equation, where you have d omega, which is the differential solid angle, so it's a small solid angle. And we have dAn, where an is the surface area perpendicular to the angle of viewing, and r is the distance from a point to the area an. So again, you can see that this is the hemisphere that I was talking about, where radiation is going to be emitted throughout that hemisphere. But to determine how much radiation is at a certain direction, we're going to have to figure out what the radiation intensity is. But you can see, if you look at this figure, this is our solid angle here. Okay, so this is why we need to define the solid angle. And then we have this area here, which is your AN. And of course, the distance R is from here to your solid angle. Okay? So this is all just some math, probably from Calculus 3. And we know that the area is going to be ds, which is r d theta times r sine theta d phi. And that gives you this area ds. And then if you want to calculate the solid angle, d omega is ds over r squared, where we said ds is r squared sine theta d phi. So you get d omega to be sine theta d phi. So we will need to use the solid angle to actually find out what the radiation intensity is, and that will eventually lead us to the radiation view factor, which I'll cover in the next video. So let's just finish radiation intensity. So the radiation intensity is defined as I, which has units of watts per meter squared steradian. And it's defined as the rate at which radiation energy is emitted in the theta phi direction per unit area, normal to this direction, and per unit solid angle about this direction. So it tells you how much radiation is in a specific direction per unit solid angle. And that gives you this equation. And the radiation flux, which is E, which is dq over dA, we can get by rearranging this radiation intensity equation to get something like this. So this would be your radiation flux. And you can see how it depends on the directions. And we can integrate the radiation flux for a hemisphere. And what we get is pi times IE, and to get the radiation flux. And for a black body, the energy is pi IE. So this is for a black body. We'll go over radiation factor in the following video, but make sure you try to understand the radiation intensity. If you have any questions, you can feel free to send me an email, and I'll be happy to respond. Until then, I'll be preparing the second video for you guys to watch. Thank you very much.